Saturn's main rings, the A, B, and C rings, alongside the Cassini division, are massive water ice structures. Combined, they contain more total mass than the planet's moon, Mimas. The entire main system resides within the classical Roche limit, extending roughly 140,000 kilometers from the planet's center. At this proximity, Saturn's tidal forces overpower the internal gravity of a fluid body, preventing material from coalescing into a single moon. Early planetary scientists operated under what we call the primordial assumption. They modeled the rings as ancient, static remnants left over from the condensation of Saturn's initial subnebula. Because the sheer scale and structural stability of the rings appeared permanent through early telescopes, observers concluded the system existed unchanged for 4.5 billion years. Treating the rings as static celestial architecture ignores the violent, transient fluid dynamics actually operating inside the Roche zone. The mechanics of kinematic viscosity and ballistic transport dictate that the rings are actively decaying. Physically, the system operates on a timeline of less than 100 million years. However, injecting a Mimas-scale mass of ice into the Roche zone within the recent geological past defies statistical probability. This split-screen timeline visualizes the contradiction. Left, physical decay limits the rings to a 100 million year lifespan. They should already be gone or entirely darkened. Right, statistical scarcity requires billions of years of waiting. The impact rate is too low to have produced fresh rings recently. Resolving this paradox requires dismantling the equations driving the physical decay and re-evaluating the actual mass and accretion behavior hiding within the ice. Saturn's rings do not behave as an ideal gas. They are a granular fluid characterized by dense packing and constant, inelastic collisions between trillions of individual ice particles. This cross-section models Keplerian shear. Because particles closer to Saturn orbit faster than those further out, the differential speeds create continuous friction. These collisions damp vertical velocities, transferring angular momentum and forcing the disk to flatten. This continuous transfer of momentum generates kinematic viscosity, which forces the entire ring system to slowly spread radially over time. We map this expansion using a diffusion time equation. The radial spread of any single particle operates as a random walk, driven directly by the viscosity of the local environment. During its mission, the Cassini spacecraft captured specific viscosity measurements of the outermost section of the main system, the A-ring. Applying the diffusion equation to Cassini's data yields a strict physical limit. The A-ring will double its current width in a mere 240 million years. The current tightly bound spatial boundaries of the rings are incompatible with a 4.5 billion year lifespan. Viscous spreading should have pushed the A-ring well beyond its current limits long ago. The rings also function as a massive cosmic dust analyzer. Their immense surface area to mass ratio catches a continuous inbound flux of meteoroids originating from the Kuiper belt and the Oort cloud. These projectiles strike the ice at speeds exceeding 30 kilometers per second. The impacts instantly vaporize the target area, expelling an asymmetrical cone of ejecta. This schematic traces a mechanism known as ballistic transport. The massive yield of prograde ejecta displaces the material, carrying both mass and specific angular momentum inward across the ring system. This process continuously strips angular momentum from the inner C-ring, causing its material to gradually bleed out of orbit and fall into Saturn's atmosphere. The impacts also carry a compositional consequence. The pristine water ice of the A and B rings steadily accumulates carbonaceous darkening agents from the vaporized meteoroids. Based on the measured rate, the pollution threshold is severe. The rings would reach complete neutrality, turning entirely dark, in 300 to 400 million years. The current high albedo and momentum state of the rings confirm the viscous spreading timeline. Structurally and chemically, the physical system appears less than 100 million years old. Forming a young ring system requires a specific initial condition. An inbound interloper object must completely shatter a pre-existing Mimas-sized moon located deep inside Saturn's massive gravity well. The physics of catastrophic disruption scales steeply. To destroy a 200-kilometer-wide solid icy moon, the incoming comet must be at least 20 kilometers in diameter. This collision probability equation models the likelihood of that exact strike. We place the target moon at 10 to the 5th kilometers from Saturn to calculate the impact variables, accounting heavily for the planet's gravitational focusing effect. We map the current population of the scattered disk into the equation. There are approximately 500,000 comets active in the reservoir, large enough to trigger the disruption. The mathematical output is stark. A destructive impact on a ring progenitor occurs exactly once every 150 billion years. If we isolate the required 100 million year physical lifespan of the rings, the specific probability of this comet strike occurring within that brief window is just 6 in 10,000. The paradox is absolute. The physics of decay demand a recent birth, but the statistics of the solar system render a recent birth impossible. These conflicting timelines rely on a single flawed assumption, that we accurately know the total mass of the rings. Historically, physicists calculated the surface mass density of the disk by measuring its optical depth. Early spacecraft like Pioneer 11 attempted to measure this optical depth by recording the light of background stars as they passed behind the ring plane. When stellar instruments scanned the B ring, light transmission flatlined at an optical depth of 4.9. Models reveal this is caused by self-gravity wakes, opaque aggregations of ice. Early occultations only measured the empty gaps, severely undercounting the mass. Cassini's advanced dynamic modeling indicates the true mass of the B ring is 4 to 10 times higher than those early optical measurements calculated. This hidden mass alters the decay models. A significantly higher surface mass density gives the ring the physical bulk needed to absorb meteoroid pollution and resist viscous spreading over drastically longer timescales. By factoring in this hidden mass, the timeline expands. The ring's origin can be pushed back 3.8 billion years to the late heavy bombardment, an era when the cometary flux was actually dense enough to routinely destroy a progenitor moon. If the rings are ancient, we have to address the final contradiction. Why do they possess highly dynamic, evolving microstructures that make them look geologically young? The classical Roche limit is not a strict boundary of absolute destruction. It is a transition zone where tidal shear from the planet competes constantly against the gravitational sticking of local particles. This geometric model maps the phase-space constraint of accretion. Particles can stick together, despite the tidal shear, if they fit securely inside the collective gravitational boundary known as the Hill sphere, represented by an aggregate radius threshold of 0.691. This localized, creeping growth results in the constant formation of temporary rubble piles, classified as dynamic ephemeral bodies. These ephemeral bodies routinely grow large enough to create visible macroscopic structures, such as the propeller wakes located in the A ring and the translucent clumps embedded in the F ring. Eventually, tidal shear or subsequent collisions shatter these larger bodies, redistributing their ice. The fragments simply accrete again elsewhere in a process of cosmic recycling. This exact mathematical balance between fragmentation and reaccretion continuously scrubs the surfaces of the ice, resetting the evolutionary clock of the individual particles. Saturn's rings operate as an ancient, steady-state geophysical system. Their youthful appearance is not the artifact of a recent creation event, but the direct result of relentless, ongoing geological renewal.